All right, this lecture is on the geology of the United States. We've taken geology and look at mountains, plains, flatlands, and we've divided the United States up into 10 different geological provinces. California in the western United States, believe it or not, is its own geological province. In fact, you can actually take the state of California and divide it further, because the geology in California is quite unique compared to what the rest of the United States. And we'll see that in our next video when we talk about just California geology and get into environmental geology. Especially with pertaining to California. So the 10 major geological provinces are the Coastal Plains. It's the southeastern United States. Basically the seaboard, eastern seacoast. Behind that is the Appalachian Mountains. Believe it or not, the Appalachian Mountains, and through erosion, deposited the material that made the coastal plain. So the coastal areas of Virginia, North Carolina, South Carolina, those sorts of states, basically is due to erosional material that came off the Appalachian Mountains. The Appalachian Mountains were formed when Pangea formed, when the African continent collided with the North American continent, which formed the Appalachian Mountains. We're going to look at the Laurentian upland. This is some of the oldest rocks in the continental United States. This is what's called the Precambrian Shield. Very stable. Not a lot of tectonic activity that has really gone on in those regions for quite a long time. That extends all the way up into Canada and over into Greenland. So the Laurentian upland, this is very old rocks. The interior plains, these are the flatlands, the farmlands of today. Basically the corn belt, the wheat belts. Underneath Kansas, underneath Nebraska, is very poor soil, salt, because that interior plains of the United States was, for a good part of its life, throughout the Mesozoic, the Paleozoic, empty continental seas had flooded this area, depositing rocks like limestone and gypsum, salt rock, not good for soil. How did this area get good soil? Glaciers brought down crushed rock from Canada. Five different glacial transgressions from Canada. As these glaciers moved very slowly, a few inches per year, they eventually made it all the way down as far south as Kansas. They brought with it a bunch of rock. They crushed that rock. That happened 5 different times, and over periods of a few million years, or actually hundreds of thousands of years, that crushed up rock became very good soil. Then we'll look at the interior highlands. This is the Ozark Mountains of Arkansas and Missouri. After that, we'll look at the Rocky Mountains, Colorado, New Mexico. The Rocky Mountains are a fairly young mountain range compared to the Appalachians. The Appalachians were formed right at the end of the Devonian. So the Devonian is a geological period of time that started 409 million years ago and ended about 354 million years ago. That's when the Appalachians were formed. The Rocky Mountains were pretty young. They started forming about 70 million years ago. So in relationship, 70 million years to 300 million years, it's a pretty young mountain range. Then we'll look at the Colorado Plateau. This is where the Grand Canyon is now situated. The Grand Canyon has actually cut down through this plateau of rocks, exposing those rocks. The Basin and Range is in Nevada and Utah. It has been formed primarily due to normal faults and extensional tectonics. Believe it or not, the San Andreas Fault is responsible for the geology we see today in Nevada and Utah, where you see a valley and a mountain range, another valley. The Colombia Plateau to the northwest, this is basically all of western Oregon, all of western Washington, and parts of Idaho. These are flood lava basalts. And then the Pacific Mountain System, the author of your book, Charles Fletcher, kind of grouped basically Canada along the western edge, all of Washington, all of Oregon, and California as the Pacific Mountain System. And yeah and no, it should really be subdivided a little bit more. We'll talk about that in the next video. So this is a map showing those regions. Here's the Coastal Plain, the entire state of Florida, eastern seaboard. Here's the Appalachians, which really do continue down into Georgia a little bit more. This is the Ozark Mountain uplift. These are the interior flatlands. The oldest rocks right here. This is the Colorado Plateau. This here is the Basin and Range, Rocky Mountains. The Colombia plateaus, which is all basically a whole sequence of lava flows. It really kind of goes into a little bit more further to the west. And then of course we've taken the entire western seaboard, California, Oregon, Washington, and broken it up into this. And if you look at, there are mountain building events which we call orogenic belts. And in the Western United States, look at all this. We had the Antler orogeny, the Sonoma, the Vaden, the Sevier, and the La Madre. Each one of these is a tectonic event that resulted in the uplifting or the formation of mountains. Pretty neat. Over where we find the Appalachian mountain belts, we had the Taconic orogeny, the Acadian, and the Alleghenian orogenies. All three of these basically represent when Africa slammed into North America. There was a piece of oceanic plate that first subducts, it melts. Then the continents come together and they separate again. A little bit of uplift goes on. So there's three different tectonic periods that result in the formation of the Appalachian Mountains. There's Ouachita organic belt here. This is when South America slammed into the Gulf Coast, or the city of the Gulf Coast, forming and uplifting the Ozark Mountains. So areas that have these orogenic belts is where you find mountains. In the stable part here, in the mid part of the continent, not a whole lot really going on. No tectonics. You don't find anticlines and synclines. You certainly don't find mountain ranges. But we do find very good farm soil. And we find the Great Lakes. And the Great Lakes are there because glaciers actually carved out those lakes. So look at every one of these different areas in a little more detail. So the oldest portion is what we call the Midwest. So this is basically Upper Skate, Michigan. Well, the next slide is going to show a map. You'll see this red rock. And this is the very old rock. It's called a red granite. It is from the Precambrian. It has been around for a long time, and this is why they call this the Precambrian shield, which basically means that this is rock that has not been subject to a lot of tectonics. It's been around for a very significant period of time. So the Precambrian granites are part of the stable interior United States, in which we call the Laurentian province, the Laurentian uplift. Another thing that you find in this region too is a formation called banded iron formations. And banded iron formations were formed at a time when the Earth had very low atmospheric oxygen, unlike today. During Precambrian times, there was a time when there was insufficient oxygen to support life. And that first oxygen that was introduced in the atmosphere was done through blue and green algae. And as life started taking a hold on Earth, more and more plants, more oxygen was put in the atmosphere. Oxygen is very unstable. It likes to bond to other things. So if it wasn't for plants, we would have no oxygen. If we removed all the plant life on Earth, all of photosynthetic life, we would soon run out of oxygen. So we need plants, we need green photosynthetic plants to produce oxygen. And that's a blank screen. So here is a map showing, so these different colors on this map are different ages. So yellow rocks tend to be very young rocks. The really deep red rocks here are very old rocks. And these are some very old rocks. And we even find some very old rocks in Nevada and in eastern California. These are rocks that came from another continent. They're part of a sequence of igneous rocks called Rabicavi granite, which is why we know that basically the Western United States all came from someplace else. So if you look at geology, you can see where things kind of correlate, all fit together, except for the Western United States. The geology here is all messed up. And that's because we are a series of microcontinents that stuck themselves onto the North American continent. We call this accretionary tectonics, and that'll be for the next lecture. So this is what these granites look like. They're red, they're very rich in potassium feldspar, but this potassium feldspar is really, has a little bit of iron in it. So the K-spar you saw in lab, that pink colored rock, it consists of potassium, aluminum, and silica. This K-spar here also has some iron in it. And it was formed at a time when Earth's crust was fairly young still. These are some very old granites, some of the oldest granites that exist on Earth. And like I said, this granitic block, which is 3.5 billion years old, goes all the way up into Canada, Nova Scotia, and even into Greenland. Greenland continent is a huge hunk of this red granite. Very old, very stable. Banded iron formations, as I said, these are formations that occurred prior to the Earth having atmospheric oxygen. If these iron formations had formed during an Earth with rich in oxygen, that oxygen would oxidize those iron formations and they wouldn't be existing. It'd be basically a big hunk of red clay that was rich in iron. So we see these banded iron formations, and they basically go all the way back between 2.4 and 1.8 billion years ago. There's a whole sequence of these banded iron formations. The old ones are basically horizontal and flat, and then they get into the younger formations in the Cambrian, and they're all stirred up and mixed around, and we attribute that to organisms, worms, burrowing down into the dirt, stirring up the sediment. And so banded iron formations, they appeared at a time basically when the Earth did not have sufficient oxygen. And at that time, we think that the Earth also, because there was a supercontinent that stretched from the North Pole to the South Pole, it restricted ocean circulation, and so Earth actually went into a snowball Earth at the time that the banded iron formations were formed. So Earth was cold, not a lot of oxidation going on because there was no oxygen, and when things are cold, the whole process of weathering and oxidation slows down. So this kind of fits that snowball Earth hypothesis. So the Eurasian uplift is mostly Precambrian granites and banded iron formations. Those are the two main units that we see in that area. This next picture will show these banded iron formations. This was an economic important discovery because this led the Industrial Revolution. They discovered all this iron, and this is what was the mineral wealth that allowed the United States to go into an industrial revolution, build railroads and cities and all sorts of cool things. And what you see here is this is a layer of hematite and shale. So the light colored stuff is a shale rock, like a clay stone. And then the dark rock here, the red rock, is the oxidized iron. Now it's being oxidized today because of the fact that we have oxygen on Earth. And these were formations that were buried, so they were out of way of oxygen. We have laterally, cut down through this material in order to extract this as an ore. And this is actually, picture was actually taken in an open pit mine. They've been mining this iron deposit here for the past 150 years. It's an important source of iron for the United States. So recent glacial carving resulted in the formation of the Great Lakes. That's kind of an interesting thing. So I said that this area was pretty stable tectonically, and it has been. Glaciers over the past 600,000 years, there's been 5 glacial advances that started in Canada, and they worked their way to the south. We named those glaciations after states that they actually glaciated, such as one of those glaciations is called the Kansian. There's the Nebraskan glaciation. The last one that occurred that ended about 12,800 years ago was the Wisconsin glaciation, because it heavily glaciated what is today the state of Wisconsin. So these glaciers kind of came in and they polished rock, they flattened it, and they brought down with it all the crushed granite. So what's in a granite? Iron, magnesium, potassium. Those are the kind of minerals you need to develop good farm soils. And we see that today in the interior plains of the United States, in places like Ohio, Nebraska, Kansas. Very good farm soils. Underneath those farm soils are salt deposits, because most of the geological history of the mid part of the United States was very shallow oceans that flooded over the North American continent, producing rocks like gypsum, limestone. Those types of rocks, calcium carbonate, calcium sulfates, they don't make good farm soils. They're void of iron, potassium. And so glaciers were responsible for that. So glaciers basically carved out the Great Lakes. They brought down with it rich, crushed up granite that would then weather out and to form very good soils. So very good soils. This is our corn belt, wheat belts. And as it turns out, the glaciers carved out the Great Lakes, and it kind of changed climate. So there's like little microclimates. Buffalo, New York receives more snow than Anchorage, Alaska. And the reason for that is that cold Arctic air comes across Canada. When that cold air picks up the moisture of the lakes. So these are big bodies of water. That moisture is then picked up with that cold air. That cold air then contacts the land. And that cool moisture then warms up a little bit. And you get these snowbanks on the opposite side of the lake. So there's no snow, not as much snow on this side. The greater accumulation of snow is on the leeward side, where the wind is coming across the lake, deposits snow, which is why Buffalo, New York sets records all the time for the amount of snow accumulation. So the coastal plain, this basically formed because the Appalachian Mountains are the result of continental collision between the North American plate and the African plate. So Pangaea formed, and then when Pangaea broke apart, the Atlantic Ocean opens up, the Appalachian Mountains stayed with the United States. In fact, even part of the African continent stayed with the United States. And then since that time, since Pangaea broke apart 200 million years ago, in the middle of the Mesozoic, erosion has taken place, resulting in sediment being deposited, forming that nice coastal plain. So the eastern seaboard of the United States is completely different than the western seaboard along the Pacific. Very cliffy, where along the eastern seaboard you have a large continental shelf. You have much larger beach areas because there's a lot more streams that carry sediment out into the Atlantic Ocean, and then the longshore current picks up that sediment, and then waves deposit the sand on the beaches. Western United States, California, we don't have as many streams, we don't have as much rainfall, and we've also dammed every one of our streams. We'll talk about that at a later date. So basically, there was a pre-continent, supercontinent before Pangaea. It breaks apart. Pangaea forms, and then by the end of the Devonian, 350 million years ago, Pangaea is formed, and at that time, this is when the Appalachian Mountains were formed, and then 200 million years ago, Pangaea then broke apart right in the middle of the Mesozoic. So this is that coastal plain here. It includes all the state of Florida. So the entire state of Florida is limestone, and a good part of its life, up until about maybe 12,000 years ago, Florida was actually underwater. And there are parts in Florida, like when you drive across Florida here in this lower part here, you get some real high elevations, like 3 feet above sea level. So Florida is a very low-lying state. If there's ever a situation where all the glaciers melted on Earth, they say that Florida will be completely flooded again and it'll be underwater. So this shows the rifting of North America, so you can kind of make out some states. Here's Illinois, Ohio, Pennsylvania. And so as the North American continent and the African continent rifted away 200 million years ago, opens up the Atlantic Ocean, the Appalachian Mountains, which used to be a coastal mountain range, as this ocean opened up, erosion takes place, depositing sediments out there, forming that coastal plain. So Pennsylvania has a lot of metamorphic rocks. In fact, Pennsylvania is known as the Keystone State, just like California is the Golden State. Pennsylvania is known as the Keystone State. A lot of metamorphic rocks because as Pangaea starts to form, there was a piece of oceanic plate between the African continent and the North American continent. That oceanic plate subducts and goes underneath the United States. That melted plate is then going to come up in the form of plutons, magma. That magma is going to touch, make contact with existing sedimentary rocks. And this is why you see throughout the Appalachian Mountains a lot of metamorphic rocks. The entire state of Pennsylvania is mostly slate. A lot of different slates in Pennsylvania. A lot of metamorphism occurred there. Anthracite coals, there's slates, there's schist, there's gneiss, the whole sequence of metamorphic rocks. We don't have as many metamorphic rocks in the western United States, primarily because they were destroyed. The rocks that form the Appalachian Mountains have been preserved, and we see these huge belts of great metamorphic rocks. And this is due to subduction. So basically that's what you see in the Appalachian Mountains. So this entire area here is, its existence is because an oceanic plate went underneath the North American continent, melted, came up, and intruded as granitic material. That granitic material is going to make contact with the existing rocks, the shells, and metamorph those into slates. More extreme metamorphism is going to take that slate, turn it into a phyllite. The phyllite is going to turn into a schist. The schist then can become the gneiss. So this is what we see along the Appalachian Mountains, these kind of folded belts of metamorphic rocks. And they are a good indicator of continent-to-continent collision and ocean-to-continent subduction. So first we had ocean-to-continent subduction, and then when Africa joined to complete the Pangea puzzle, and that was the last piece that kind of came together, we formed our Appalachian Mountains. Okay, the interior plains, largely undisturbed, no mountain building events. Pretty much flat country, so you drive across places like Kansas, Nebraska, it's pretty flat. There aren't any mountains because they haven't had any tectonics. It was certainly, most of its life, they were flooded by epicontinental seas, so epicontinental means basically a very shallow sea. These were seas that formed during the Paleozoic, when the North American continent was right at the equator. So these were very warm, shallow seas. They deposit a lot of evaporites, so things like halite, gypsum. And we had basically two periods of these epicontinental seas, one in the Paleozoic, throughout the Ordovician, and then in the Mesozoic and almost into the Cenozoic, this part of the United States was still flooded. And it wasn't until recently when the Rocky Mountains start to uplift that also the interior plains uplift, but not to the significant event that it causes mountain building, and that forces the epicontinental seas to drain off. So this is this entire area here, pretty flat country. It's also called the stable craton because of the fact that there are no mountain events. There's no really mountain building events. They kind of make a little bit of stretch here. The Hudson orogenic event basically occurred when the African continent hits the eastern seaboard of the United States. It creates the Appalachian Mountains, and it caused a little bit of a rippling to occur. So to the point where you have some basins and domes. The entire state of Michigan is a great big basin. It's a very gentle basin. Today we're exploring these basins because they're very important for natural gas. Natural gas is accumulated in some of these basins, so we have little slight downfolds and slight upfolds, like the entire state of Missouri is a slight dome, an upfold. The entire state of Michigan, the entire state of Illinois are basins. So this is what they're talking about when they talk about the Hudson orogeny. It's kind of a stretch to really call it an orogenic mountain building event because there really were no mountain building events that occurred there. So this is what the central part of the United States looked like for most of its life. This is the Paleozoic. So here you can see the outlines of some of the recognizable states. Illinois again, Wisconsin, Colorado, New Mexico. Here's Arizona. Notice that there's nothing here past Arizona. There is no Nevada yet. There's no California. These light blue colors and this white area is very shallow seas, very warm seas. A lot of halite is being deposited, a lot of salt rock and gypsum. And then over time, as Pangea breaks apart now, the North American continent starts to rift away from the African continent. On the western United States, during the Jurassic, the Cretaceous, subduction is occurring. Little microcontinents are beginning to stick themselves onto the North American continent. That creates a ripple effect, and the land starts to uprise. There's a big uprising. And the seas are eventually, this is actually called the Sundance Sea during the Mesozoic, is eventually going to drain. So that's this entire area here. And then glaciers. Over the past 600,000 years, they start in Canada, and as this ice accumulates year after year after year, it then, due to the compaction and the weight, the glacier then starts to move south. So these glaciers start in Canada. The next slide is going to show the extent of glaciates that occurred. These glaciers then move And as they move, they bring with it rock. They crush that rock up, they pulverize it, then it is exposed to the elements of weathering, chemical weathering, and then the formation of good farm soil. So some of the best soils in the world occurred because of glaciers, and we find them in the interior part of the United States. So we basically can attribute this to glaciations. So the glaciers already start up in Canada and then move southwards. There were 4 major glaciations. The most severe, the most southern one, was the Kansian glaciation. And so the glaciers would advance, climate would warm, they would retreat. Climate cools up again, the glaciers advance, then they retreat again. And we saw this occurring 5 times over the past 650,000 years. Each time, these glaciers brought with it crushed rock. And it's granite it was crushing. And granite rocks, like I said, they're rich in iron, magnesium, potassium. Those are the type of elements that you need to form really good soils. So here's the extent of the last glaciation, the Wisconsin glaciation. So ice basically gouges out the Great Lakes and deposits all of this rock that we stole from Canada, deposits it in the United States, and what is today the United States. So the farmland of the Great Plains is glacial outwash sediments from glaciers. The wheatlands and the cornfields of the interior part of the United States, they would not exist today if it wasn't for glaciations. What's underneath that good farm soil is gypsum and salt, and you cannot grow corn, wheat, you cannot grow good crops in that type of soil. It's just a terrible soil. So this is the Great Plains farmlands. You'll find a lot of lakes. And we owe our farmlands to glaciers. Interesting how it basically dominates a good part of the United States. Also, while glaciers were carving out and depositing rock in the interior plains, glaciers were actively carving out the Rocky Mountains. So over the past 600,000 years, the Rocky Mountains were probably twice as tall as they are today. So their mountain range is relatively young, about 70 million years old. Glaciers also were very actively eroding the Appalachian Mountains. Those mountains are much older, and so mountains are being torn down by glaciers at the same time that soil is being developed in the interior plains. So the Rocky Mountains. Interesting thing about the Rocky Mountains is you find these very tall mountain ranges, and at the top of those mountain ranges, you find seashells. You find fossils that are marine. And so there's kind of a couple of ways in which the Rocky Mountains form. First, during the Proterozoic, so this is Precambrian, Rhodney and smaller continents start drifting in and start attaching themselves onto the western United States. So we have marine sediments that were deposited, and then because of continental collision, those marine sediments are then hoisted up into mountain ranges. So that's why we find marine fossils at 10,000 feet elevations in the Rocky Mountains because of this uplifting. So there's a small microcontinent. This basically, Rhodia, was a small piece of Gondwana land. So Gondwana land, so when Pangea broke apart, it broke up into 2 major continents. Laurasia, which consisted of North America and Europe and Asia. Gondwana land consisted of South America, Africa, Australia, Antarctica, and India. And then a part of that rifted away, basically Australia and Antarctica, and then Australia is going to rift away. That's kind of the breakup of a little continent, a little microcontinent called Rhodia. So Rhodia is really Australia, maybe some pieces of India, which is now way north. And this is later going to collide with California, creating great tectonic activity. This is what's going to uplift the Sierra Nevada Mountains, the San Gabriel Mountains, the San Bernardino Mountains, the Rocky Mountains. So we had deposition of eroded sediments from this breakup of Rhodia, a lot of sedimentary rocks, shells, limestones, and then this continental collision. This basically uplifts these sediments to form the Rocky Mountains of today. So the Rocky Mountains that we see today, a lot of these high peaks were twice as tall, but over the past 650,000 years, glaciers have cut through these mountains exposing them. Basically, this is a good example of mechanical erosion, glacier ice. Ice is very heavy, very dense, carving along. And the interesting thing about the Rocky Mountains is that when you drive across the plains of the United States, across Kansas, and you come to Colorado, eastern Colorado is pretty flat, and it grades up slowly to Denver, which is 5,280 feet above sea level. And then right at the edge of Denver is this big tilted, uplifted section called the Front Range. And it's often baffled people like, wow, the land is flat, and then all of a sudden, boom, uplift, you got the Rocky Mountains. And they think that this was a weak part in the continent, and when all those microcontinents kept slamming into the North American continent, it caused a rippling effect. And this is a soft spot, or a weak spot, in the United States, and this is where these rocks bent. And this basically is the boundary. The Front Range is the boundary between the Rockies and the plains. So the Rocky Mountains were formed because of continental collision. Part of the Rocky Mountains, and within that is, and this next slide will show the subdivisions, really the Colorado Plateau is part of the Rocky Mountains, but it did not act like the Rocky Mountains. You see, the Rocky Mountains, if you look at them, the rocks are tilted. So they once were flat, they've been tilted like this. The Colorado Plateau doesn't resemble that at all. These are basically a whole sequence of Paleozoic marine sediments that go from the Cambrian all the way up through the Permian 250 million years ago. So you have rocks, there's this whole sequence of rocks undisturbed. Underneath those Paleozoic marine sediments are metamorphic and igneous rocks. Some of those are tilted due to prior tectonic events, but the Colorado Plateau kind of uplifted uniformly, very slowly, without folding, without tilting, which is kind of unique. So you kind of have this time capsule within the middle of the Rocky Mountains that was not subject to the tectonic activity that the Rocky Mountains were. It didn't act in the same way. So this is this area here, G. It really is part of the Rocky Mountains. The reason they subdivided this and called the Colorado Plateau is because the geology, even though the same rock types you find in F, you find marine sediments, you find the same marine sediments here, the difference is that these marine sediments are flat, they're horizontal. They have not been subject to the tectonics such as thrust faults, reverse faults. They have not been tilted. They're pretty flat laying marine sediments, and we see this in the Grand Canyon. So we have these exposure Precambrian basement rocks. We have the Zoroaster granite. We have the Vishnu schist. These are the rock formations. And then overlying those Precambrian rocks are Paleozoic rocks consisting of sequence of rocks, sandstones, shells, and limestones. And those rocks represent a transgression of the oceans that flooded what is today northern Arizona. That happened several times. Interesting thing is that this is a meandering stream. When we talk about fluvial systems in the previous lectures, I told you that meandering streams like this occurred on flatlands. You see this in the Mississippi River. You go to the Mississippi River, and that's a river system that meanders back and forth like this. So the question that baffled geologists is like, wow, what is a meandering stream doing in an area with mountains? And one of the hypotheses is that this was a flat land with meandering streams, and that the Colorado Plateau uplifts very slowly. It doesn't increase the gradient of the stream, because if you increase the gradient of the stream instead of meandering would go straight. And this is why within the San Juan River and parts of the Colorado River within the Colorado Plateau have this meandering effect, because this was a flat plain that uplifted very slowly without the tilting, without the thrust faults, the reverse faults, or even normal faults. It just uplifts uniformly, very slowly, allowing the Colorado River, the San Juan rivers to cut down through these sediments and to maintain this meandering type stream. So uplift did not have a significant gradient change, and so this meandering system within a canyon is very unique. There's only one other place we see this in the world today, and that basically is in Australia. They're almost the same sequence there. So meandering stream in a mountain area is very rare. The interesting thing about the Grand Canyon is the Grand Canyon has all three types of unconformities. It has, at the very bottom, a nonconformity. This is where sedimentary rocks are in direct contact with igneous rocks. So sedimentary rocks cannot touch the igneous rocks because they should have been metamorphosed. So shales should have been turned to slates. So that's why we call it a nonconformity. There's an angular conformity where you have tilted rocks that are overlying by flat rocks. And then throughout the Grand Canyon we have some disconformities where parts of the geologic record are completely missing. A good example of that is at the bottom of the Grand Canyon. You go from Cambrian rocks. You don't find Ordovician, you don't find Silurian rocks, but you do find Devonian rocks. So that means the period of time from 500 million years ago to 409 million years is just missing. And this is what we find in the Grand Canyon, all three types of unconformities. So the Grand Canyon, these rocks are flat, they're horizontal. They haven't been subject to folds like into anticlines or synclines. There haven't been any thrust faults. It's a unique geological setting, and these sediments that go all the way back to Precambrian time, and then the marine sediments are from the Cambrian all the way up to the Permian. So you have a nice textbook example here. You have a good chronological sequence where you have rocks that go all the way back to Cambrian, 540 million years ago, throughout the Ordovician, the Silurian, the Devonian, the Carboniferous, and then the Permian. Except there are some disconformities where part of the record is missing. And so all three unconformities, we have the angular conformity, we have the disconformity. So in the Grand Canyon, the disconformity is there because you go from Cambrian to Devonian. So you're missing basically Ordovician and Silurian rocks. They're just not there. So Ordovician is a period of time between 500 and 435 million years ago. The Silurian is between 435 million years and 410, somewhere in that ballpark. That sequence of time is missing. And so are the fossils, which is why we know that that strata is missing in the Grand Canyon. And the nonconformities where sedimentary rocks are in direct contact with igneous rocks. So we have all three unconformities in the Grand Canyon. So this kind of is a picture that shows this. So here we have the Precambrian rocks. And what we should have here, after the Precambrian, we should have Ordovician. We should have Silurian. And then Devonian, and then even part of the Mississippian and Pennsylvania. Part of the Mississippian is missing. So the Mississippian is a period of time that went from 354 million years ago to about 325 million years. But even the Mississippian in the Colorado and the Grand Canyon is missing. And in we're actually doing a lab where we actually look at the Grand Canyon, and we'll see these disconformities. So the Grand Canyon, all three unconformities. Angular, where you have tilted rocks that are overlying by flat rocks. We have a nonconformity, where sedimentary rocks are in direct contact with granitic rocks. And then we have the disconformities, where part of the period is just missing. Part of the time record is just plain missing. Basin and Range. What forms the Basin and Range in Nevada, Utah, Arizona, New Mexico is the San Andreas Fault. So because the San Andreas Fault is stretching the North American continent, it's actually stretching it, and it's causing a whole sequence of normal faults to down drop these basins. And we call this type of topography Basin and Range, or Horst and Graben. So Horst and Graben. Basins drop down along normal faults, the mountains stay up high, and you see a huge elevation change. So a good example of that, Death Valley, where Telescope Peak is right around 9,800 feet above sea level. And then when you stand there in Death Valley, you can sit there, and it might be, in springtime, it might be 90 degrees there. The elevation there is 283 feet below sea level. You look across the valley, you see Telescope Peak that's almost 10,000 feet with snow on it. Huge change in a very short distance. And that's called the Horst and Graben tectonic activity. So that is basically all of Nevada. It does extend up into a little bit into Idaho, a little bit into California. It does continue down to Mexico, into extreme western Texas. All this pink area here is what we call the Basin and Range, or Horst and Graben. So this is tension and extensional tectonics resulting from the San Andreas Fault. So the San Andreas Fault contacted the North American continent about 27 million years ago. From 27 million years ago to today, this is still ongoing, the North American continent is being stretched. And as it has been stretched, these basins are being downdropped, and they're continuing to downdrop, which is why places like Nevada, Las Vegas, Phoenix, Arizona, they have potentials for earthquakes there. And they haven't had any in historic times, unlike California. And so these areas do have a good potential for earthquakes. So this Basin and Range, southwestern California, the entire state of Nevada basically, Utah, it goes into Arizona, New Mexico, and all the way into Texas. Huge area of extensional tectonics. So this basically shows how this occurs. The rocks are stretched. As they're stretched, they crack. More stretching, more tension. Those cracks begin to open up, and the basins will downdrop. And it forms this topography called Basin and Range. We see a basin surrounded by two mountain ranges. So here's the basin, mountain range, mountain range. And you see this if you drive out to the river on I-40. You'll go up over a mountain, go down to the basin, up over another mountain, then to another basin. And this is typical of the landscape of the Mojave Desert, Nevada, Utah, southern Arizona is this way. And this is all due to the San Andreas Fault stretching the landscape, which is pretty intense. So this is actually Death Valley. The reason we call this Horst and Graben is the mountains are like the horse. They're pulled up, or they're wore up, and they stay there. So it's hard to imagine that Death Valley, which is 283 below sea level, at one time was at the same elevation as these mountains. It has been downdropped. And this is all due to, right here, the San Andreas Fault. So the San Andreas Fault is a spreading center. It was a plate boundary between the Pacific Plate and the Farallon Plate. As the Farallon Plate got subducted underneath the North American continent, as the North American continent moved to the west, it overrode the spreading center. That spreading center is now underneath California, and that spreading center is the San Andreas Fault. So we'll let this kind of go one more time here, and I'll explain this as it goes. This is a time starting 40 million years ago. So here we go. Spreading center, Farallon Plate, subducts, melts, creates volcanoes, the Sierra Nevada mountains. And then, once the North American continent overrides this, the North American continent becomes stretched. I mean, look at what happens in Nevada and California. Look what happens in Arizona. They're stretched. So over the past 27 million years, when the San Andreas Fault made contact here, about 27 million years ago, it has been stretching the North American continent, and it continues to do that today, forming this Horst and Graben structure. So as you drive around the southwestern United States, this is actually at the California-Nevada border, mountain range. I took this picture from a mountain range. These are the McCulloch Mountains. Across this basin here is the Clark Mountain Range. And you have this basin down here with this dry lake in it. This dry lake is called a playa. Today it's a nice flat salt plan. People like to drive their vehicles across the hills at 100 miles an hour. And if you were here 12,000 years ago, when the glaciers were melting, this would have been a lake. Today we call it a dry lake or a playa. So this is typical what you see Basin and Range topography. During the last glaciation, when the glaciers were melting, 12,800 years ago, global warming kind of kicks in, glaciers start to retreat, they melt. As they melt, all that melt water is going to fill up these little basins that are being formed. So this is 12,000 years ago. It formed great lakes like Lake Lahontan, Lake Bonneville, which is a remnant of that today called the Great Salt Lake City. Out in Death Valley, the entire Death Valley was flooded this time. There was a great big lake called Lake Manly. Out in California deserts near Barstow and Baker, there was a lake out there called Mannix Lake. And so all these lakes since the glaciers have stopped melting, the glaciers are too far north now, the water supply was cut off, and the southwestern United States dried. All right, Colombia Plateau. So we have two more areas to look at. We're going to look at the Colombia Plateau, and then we're going to look at Western California just briefly. And then in the next slide presentation, I'm going to explain California just a little bit more, and we'll get into coastal California and look at what's going on with our beaches. So the Colombia Plateau is a sequential layer of lava flows. So one lava flow on top of another lava flow, on top of another lava flow. These are not explosive volcanoes. These are volcanoes, fissures actually kind of opened up, magma comes spewing out, and that magma is going to be very mafic, rich in iron. So this is not going to be an explosive volcano. This is going to be a very mild volcano like we see today in Hawaii. Very iron-rich flows, lots of iron-rich magma. This magma is going to, of course, weather into good farm soils. So today, Idaho is known as potatoes. So to grow potatoes, you have to have potassium and magnesium, because that's what potatoes have in them. They're actually a good source of food. Unfortunately, what our society does with potatoes is we like to cut them into little strips, deep fry them. French fries, right? Like at Del Taco and McDonald's and so forth. So the reason that Idaho grows potatoes, it basically has soils that have resulted from the weathering of this black basaltic rock, which is very rich in iron and magnesium, and it's the perfect atmosphere, the perfect environment to grow potatoes. Idaho produces some of the best potatoes in the world. There's a similar story can be said for Russia. Over in Russia, they have volcanic rocks at a northern latitude where it's cool, and they can, of course, grow potatoes there. And I guess the Russians use their potatoes not to make French fries, but to make vodka. So if the Russians and the Americans ever got together with their potato crops, we would have vodka and potatoes. That'd be an interesting concept. So these volcanoes basically were kind of like these monogenetic fields. They were like a bunch of little fissures opening up, very rich in iron, not explosive, low silica content, and this kind of created what was called a flood volcano. And we see this on very small fields, and we see this on very large igneous provinces. And this is what basically formed the Colombia Plateau, whole sequence of flat-lying lava flows. Just one lava flow after another after another. And so this is what that lava would have looked like. Very mafic, very flowing. And today, if you look at the Snake River, the Salmon River, these rivers have cut down through these sequences of lava flows. It's created floodplains where you have very good soil conditions and a cooler climate that is just perfect for growing potatoes. All right, the Pacific margin, the last area we'll talk about, and then we're going to go into more detail in the next lecture, and we'll kind of spend the time on California. So what I want you to know about the Pacific margin is accretionary tectonics. This means that pieces of other continents that broke away from a little continent called Rhodia came across on a plate, the Farallon plate, and the Farallon plate was like a conveyor belt, or like an escalator in a mall. All of these little microcontinents stuck onto the North American continent. So the western edge of North America grew westerly. So if you were to go back in time to the Mesozoic, there was no Nevada. There was no California. And so California and western Nevada are basically the result of subduction, accretionary tectonics. Some of the volcanoes were erupting, and basically this created what is today California and western United States. So we had this entire area here, J here, is all accretionary tectonics, which means that the land here came from somewhere else. It's not even part of the United States. It was brought in from someplace else. So we had conveyor belts, we had subduction zones, just acting like conveyor belts, bringing all this material, as this material was, some of it was subducted, the oceanic plate would certainly be subducted, it melted, it came to the surface in the form of volcanoes. That rock underneath, that magma that crystallizes into the ground is going to form granitic rocks, which are going to later be uplifted. This next picture is going to kind of show that, where you have what's called an accretionary wedge, where here you have the subduction zone, and all this material that's eroding off the continent, and these microcontinents are all kind of colliding together, and everything's going to be pushed up, and that's why we have the Sierra Nevada mountains today, the San Gabriel Mountains, the San Bernardino Mountains, the Rocky Mountains. A lot of mountains are formed at this time. So at this point in time, up until about 27 million years ago, California was being compressed. New terrains were coming. So as the North American continent moved to the west, and these accretionary tectonics came from the east, east meets west, big bulge of material, and this is where the North American continent kind of grew. Today, as of 27 million years ago, the San Andreas Fault has taken all the stuff that was compressed and pushed together, and now it's pulling it apart. So this is why California geology is so complex, because first everything was pushed together, now it's being pulled apart by the San Andreas Fault. So as of 27 million years ago, we went into a whole new era in tectonics called extensional tectonics. Old thrust faults that were pushed together when the continents were colliding are now being reactivated because they're being pulled back apart again. And we refer to these as blind thrust faults because a lot of them are buried, hence the word blind. So because we have a plate boundary between the Pacific plate, the North American plate, and the formation of our San Andreas Fault, California today is being extended. Now, if you go up into Oregon, Washington, British Columbia, they're still being compressed because there's still a remnant of the Farallon plate called the Juan de Fuca plate and the Gordia plate. They're being subducted underneath Washington, which is responsible for a mountain range called the Cascade, which is a chain of volcanoes. Starts with Mount Shasta in Northern California, goes all the way up. Mount St. Helens, Mount Rainier, Mount Baker are all part of that. And so today, if you look at Alaska, Alaska is what California looked like, say, 35, 40 million years ago. Alaska is an active subduction zone. Alaska has active volcanoes. Now, eventually what's going to happen is that the North American continent, because it continues to move west, that spreading center, which is off the coast of Northern California, Oregon, Washington, British Columbia, is going to be overridden by the North American continent. And so the San Andreas Fault is going to continue to grow. It's going to move north. It's going to go into Northern California, then into Oregon, into Washington, then British Columbia, and eventually to Alaska. So Alaska basically has a chain of volcanoes called the Aleutian Island Peninsula. So this long chain of islands here, they're actually all volcanic, and these are the result of the Pacific plate, which is subducting, going underneath the North American plate. That plate is melting, coming back up in the form of volcanoes, and this is what forms the Aleutian Islands of today. Very active volcano chain. So these are what those volcanoes look like. This is where that show is filmed, Deadliest Catch, where the people go out and catch the crab. And just to show you how active these volcanoes are, this is a satellite image that I downloaded from NASA that shows one of those volcanoes erupting. So imagine, this is what the Sierra Nevada mountains of California once looked like. What's underneath these volcanoes are magma bodies. Now if those magma bodies cool and solidify into rock, and then later uplifted, they'll be granitic mountains. And by that time, all these volcanoes are going to be eroded away. So Alaska is kind of where California was, say in the mid-Mesozoic, up until about 27 million years ago. Eventually, the volcanoes are going to go away. The continent is going to override the spreading center, and the San Andreas Fault is going to move north to Alaska. So, the Cascade Mountain Range, active tectonics due to subduction and melting ocean plates. So Alaska, the Cascade Mountain Range, those places, Oregon, Washington, British Columbia, Alaska, is kind of where the California was from basically the mid-Mesozoic all the way until about 27 million years ago. And that's the end of the United States geology. Next, our next sequence will be, we'll focus on California, a very complex and very unique geological setting. Unlike anything else in the world, California is quite unique geologically. Now people may say other things about California being unique, but hey, unique is unique, and it's actually cool. And that's all for now.